In this video, we're going to talk about section 5.1, matrices and linear systems. This is going to be part one of this section. I'm going to split it up to pages 1 through 4 in this video, and then pages 5 through 8 in a separate video. And so in this video, we're going to focus more on basic topics from linear algebra or matrix algebra. So if you are already familiar with matrices and how to work with them, you can probably fill out these notes on your own without much help. But for those of you who don't have much experience with matrices, feel free to listen on and we'll work some of these examples out. In this video, you will not see any applications to differential equations. However, in the second video over the last 4 pages is where we'll see how this relates to differential equations. So to begin, let's just get some definitions out of the way. An M by N matrix A is a rectangular array of M times N numbers. So you multiply those together, also known as elements. And the M denotes the number of rows, the N denotes the number of columns. We have this notation right here that in general we can denote a matrix first of all with those square brackets, and then that lowercase a with the subscript ij indicates what row and what column that element lives in. So again, the first subscript is always referring to the row, so the ith row, and the second subscript corresponds to the column, in this case the jth column. The zero matrix is just the matrix that is comprised of solely zeros in every single entry. We can define 2 matrices to be equal if each of their corresponding entries are equal. So we're looking at row 1, column 1, that entry is the same as the entry in row 1, column 1 of matrix B, and et cetera, et cetera. You can add 2 matrices by adding their corresponding matrices. It is important to note that it must be the case that these matrices are the same dimension M by N. Otherwise, it doesn't make sense to talk about corresponding entries. To multiply a matrix by just some scalar number C, we just take every single element and scale it by that value C. So then we have various properties here for matrices. If you take the matrix A and add 0 to it everywhere, you get A back itself. Matrix addition is commutative, and that should make sense because adding 2 matrices is just adding each corresponding entry. And since the real numbers are commutative under addition, so are matrices. We also have associativity over here in 3. We have that scalar multiplication can distribute across matrix addition, and then similarly that scalar addition distributes across a matrix. So we have those 5 properties, none of which should be super alarming. Everything just follows from properties of the real numbers. And so let's just get some practice with working with some basic matrices. You'll see matrix A and B there. Both of them are 2 by 2 matrices because they're 2 by 2 matrices because there are 2 rows and 2 columns. And so for the first example, part A, we want to find 2A plus 3B. And so what I'll do here is just begin writing this out with the matrices included. So I want 2 times matrix A, which I'm writing out here in the square brackets, and then 3 times matrix B. And so remember, for scalar multiplication, you're just going to multiply each individual element by that scalar. So 2A becomes 4, negative 6, 8, 14. And 3B becomes 9, negative 12, 15, 3. And now we've reduced it to just a sum of 2 matrices. So we're just going to add entry-wise. So for the row 1, column 1 entry, it's 4 plus 9. For the row 1, column 2 entry, it's negative 6 minus 12, and so on and so forth. I do not expect you to show this step. I'm just doing it for illustrative purposes so that everybody is following along. So we get 13, negative 18, 23, and 17. So that matrix there is our final answer for the sum of 2A and 3B. Similarly, we can do subtraction. 3A minus 2B is going to be 3 times the matrix 2, negative 3, 4, 7, minus 2 times the matrix 3, negative 4, 5, 1. So this is 6, negative 9, 12, 21. And minus 6, negative 8, 10, 2. And so now I'm just going to subtract each entry pairwise. So I'm going to get 0, negative 1, 2, and 19. All right, so those are just two quick examples of working with both scalar multiples of matrices as well as addition and subtraction of two matrices. All right, we can define what's called the transpose, and that's denoted by a superscript capital T next to our matrix. And so what that is it's taking an M by N matrix and making it an N by M matrix. And what it does is it takes the jth column of A and it becomes the jth row of AT, and so on and so forth. So you'll notice in this notation here, where A was originally denoted as the matrix with the components or with the entries Aij, now its transpose is the matrix whose entries are Aji. So we're just literally flip-flopping rows for columns to get out our transpose. So for example 2, we want to come up with the transpose of the matrices for A and B from the previous example. And so let me begin by just copying down what matrix A was up above. So that was 2, negative 3, 4, 7. And so we want to find the transpose matrix. So what I'm going to do is I'm going to take this column right here and I'm going to transpose it so that that column becomes the first row in A transpose. So 2, 4. What used to be the first column is now the first row. And then similarly, I'm going to take the second column of A and it's going to become the second row of A transpose. So this is A transpose. And I do want to note here that the diagonal matrices or the diagonal entries stayed the same. So those are the AII entries. And so when I flip-flop those subscripts, IJ, since they're the same, they stay. So the diagonal stays put in the transpose matrices. And then we could do the same thing for B. B was the matrix 3, negative 4, 5, 1. And then let's find its transpose. So the column 3, 5 becomes the row 3, 5, and the column negative 4, 1 becomes the row negative 4, 1, and there is our transpose. All right, so those are matrix transpose. We have a few more definitions here. A matrix is square if the number of rows is the same as the number of columns. Makes sense? If we have an M by 1 matrix, that means we have M rows and 1 column. We call that a column vector. And then similarly, if we have a 1 by N matrix, that means 1 row and N columns, we call that a row vector. So a single row. We're going to utilize these column vectors and row vectors to define the scalar product, all right? And so what we're going to do is we're going to take this row vector A and this column vector B, and you'll notice here that just for white space purposes, a lot of textbooks will write it as its transpose, just because then you're not wasting as many lines in the text. And so if you want to take the scalar product of the vector A and B, where A is a row matrix and B is a column matrix, it's defined right down here below. And you'll notice what we're doing is we're taking the product of the first entry in A and the first entry in B, and then we're adding it to the product of the second entry in A with the second entry in B, and so on and so forth. And holy cow, this should look familiar. This is just the dot product that we learned back in Calc 3. So these guys just are vectors. We're just writing them in terms of a matrix, but they're just vectors. And so when we talk about the scalar product, it's the same as the dot product. So we're going to be utilizing that quite a bit here whenever we're talking about matrix multiplication. And so then that brings us to how can we take the scalar product and generalize it in terms of matrices. And that's our following definition. The product of two matrices is defined only when the number of columns of A equals the number of rows of B. So notice that we have A is an M by P matrix and B is a P by N matrix. So we need those P values to be the same. Then if we want to compute their product, what it is you're using the scalar product or the dot product of AI with BJ. So we're going to continually take this row by column dot product and then add those up to get a single scalar value, and that's what's going to go in each appropriate entry in your matrix. So I think this is best understood when you just jump into an example. And let's look at example 3. We're using those same two matrices that we had in example 1. We want to find the product AB. So first, let's just write our matrices out next to each other. So here's A, and then next to it is B. And you'll notice that typically we don't put a dot or a cross or anything in between. Whenever two matrices are next to each other or juxtaposed, it's understood that you're going to apply the matrix multiplication operation. So what we would like to do is identify what should go right here in this A11 entry. That is, what should go in the first row and the first column. So how we determine that is we're going to take row 1 in A and column 1 in B, and we're going to compute their scalar product. So again, that's just the dot product. It's going to be 2 times 3 plus a negative 3 times 5. So we're doing a row times a column. And then whatever that scalar entry ends up being is what's going to be our entry in that 1, 1 spot. So let's do that again. I'll erase these lines so that they're not so cumbersome. And now I want to take row 1 by column 2. So this is what's going to go in the entry of row 1, column 2. So we're going to fill this blank in. So again, just take the standard dot product. 2 times negative 4 plus negative 3 times 1. And so now we filled in the two entries that belong in row 1. So now let's do row 2. We're going to take row 2 of matrix A, dot it with column 1 of matrix B. So what we're going to get is 4 times 3 plus 7 times 5. And then finally, we want the entry in row 2, column 2. So we have row 2 of A and column 2 of B. And that dot product is 4 times negative 4 plus 7 times 1. And so for the final step, go ahead and carry out this arithmetic here. So I have 6 minus 15 is a negative 9. Negative 8 minus 3 is negative 11. 12 plus 35 is 47. And negative 16 plus 7 is negative 9. All right, so this matrix here is going to be the product of A times B using this scalar or dot product in each coordinate. For part B, we want to do the exact same process, except for now we're finding B times A. So let's take a look at this. Again, let me just write out the matrices B and A. So B is 3, -4, 5, 1. A is 2, -3, 4, 7. And we want to carry out this product. So just to keep track, for those of you who are seeing this for the first time, I'll still go ahead and just circle which rows and columns I'm using. Whoops, let's do a row here. Row times column. All right. So for our 1, 1 entry, we have 3 times 2 plus a -4 times 4. And that's going to be our first entry. Now I want to go, oh shoot, what was that? That was a 2. All right, now we want to do row 1, column 2. So I'll circle column 2. That entry is 3 times -3 plus -4 times 7. All right, and now we'll move on to row 2, column 1. Here's row 2, here's column 1, and that's going to go in the row 2, column 1 entry in the product. So 5 times 2 plus 1 times 4. And the final computation is going to be row 2, column 2. So that is 5 times -3 plus 1 times 7. So finish off the arithmetic. 6 minus 16 is a -10. -9 minus 28 is a -37. 10 plus 4 is 14. And -15 plus 7 is -8. All right, so let me move this up just a minute. So I just want to point out here that up here we computed AB, down here we computed BA, and you'll notice something peculiar, that these products, even though we were taking the product of the same two matrices, when we switched the order, we got two different matrices. Remember, our definition of equality between matrices is that each corresponding entry is identical. And in these cases, none of the entries are equal. So this is an important property that we'd like to note. All right, so moving down, we have property 6, which says, look, you can group them differently and still get out the same answer. So we have associativity here. And we have distributivity of matrix multiplication across the sums of matrices. However, what we just discovered in this last example was that in general, matrix multiplication is not commutative. You cannot switch the order. And so this is important to note. Maybe it happens that they're equal, but that would be a fluke. It's not going to happen all the time. And furthermore, something that is kind of alarming that we're not used to is that you can get the product of two matrices to equal 0, even if neither of the initial matrices were all zeros. So it just might happen that when you take this dot product and add all of these products up, that they equal 0 in each coordinate, but that doesn't mean that one of the original matrices were 0. So these are interesting just because they're not properties that we see in the real numbers. So keep that in mind. A few more pieces of terminology here. If we're going to talk about square matrices, remember that means that the number of rows equals the number of columns. So we'll denote that in general by an n by n matrix. We call that number n, we call that number n the order. And furthermore, the identity matrix of order n is this matrix as described. So you'll notice that along the diagonal, we have all ones. And then in each of the other entries, so along these triangular corners, all of those terms are 0. So in general, that's how we're going to define the identity matrix. So this diagonal here from the top left to the bottom right is called the principal diagonal. Those are all the ones, and then everything else is a 0. And then not surprisingly, this is called the identity because when you multiply any matrix A by the identity matrix on either the left or the right, you get the original matrix A right back out. All right, so that's why it's called the identity. We would also like to understand the inverse of a matrix. That is, if you have a matrix and you want to multiply it by some other matrix to get the identity matrix back out, how would you do that? And so that is the definition of the inverse. It means that if you multiply A inverse on the right by A and also on the left by A, that you get that identity matrix back out, where the identity matrix is exactly what was defined up above. Zeros or ones on the principal diagonals and zeros elsewhere. Now we're going to roll into a term that should be familiar from Calc 3. We're going to talk about the determinant, and the determinant of a 2 by 2 matrix, where that matrix is generally speaking just denoted A, B, C, D with those entries, is you take the product of the entries on the principal diagonal AB and you subtract off the entries on the offset diagonal BC. And so the determinant is noted in two different ways. You have this det A notation, where det, of course, is short for determinant, or you have this vertical bar notation, which indicates you're taking the determinant. So I just want to note that the square brackets here is just notation for matrix A, whereas the vertical bars is the determinant of matrix A. So just make sure you're being careful about whether you do want the straight bars or the square bracket bars, because they do mean two different things. So we know how to take the matrix of a 2 by 2, or excuse me, we know how to take the determinant of a 2 by 2 matrix. How can we extend this to a matrix of larger size? And so we have our formal definition here. It says, suppose we have an n by n matrix, and we're going to let Aij denote the n-1 times n-1 strike-through matrix, or also known as a cofactor matrix. If you took Calc 3 with me, you have already seen this, because this is how I was computing cross products. But if you took it elsewhere, this might be new. How you find the strike-through or cofactor matrix is you want to delete or strike through the ith row and the jth column. And then what you want to do is you want to expand along whatever row or column you choose to compute the determinant. And this is done in the following way. So the formula is the determinant of A is going to be the sum where you're summing over J, your column in this case, and then you are computing this sum. So what does this say? First of all, we have some kind of an alternating sign popping out, a -1 to the I plus J. So that's either going to output +1 or -1, depending on whether I plus J is even or odd. Then we're going to take the entry Aij, again, we're indexing over J, so that the row is going to stay the same, but the column is changing. So we're fixing a row and moving over each entry across the different columns. And then we multiply that by the determinant of this strike-through or cofactor matrix. So the idea here is we're going to take a larger matrix and we're going to continually move down to a smaller n-1 by n-1 matrix until we get down to a 2 by 2 matrix, in which case we know how to compute that determinant we did right up here. Personally, I think looking at this definition is kind of confusing because there's a lot of subscripts going along, a lot of I's and J's. So let's take a look at, well, before we get to an example, I just want to note that this was assuming that we're expanding along a particular row. We can also expand along a column. The notation is exactly the same, or the equation. The only difference is now we're indexing across I rather than J. So you're fixing a column and then moving down or up that column into all of the different rows, and you're summing over I. Something that's important to note is that the computation of the determinant does not depend upon the choice of row or column that you expand upon. So you can pick any row or column that you want, and as I always say, make good choices. If you see a row or column that has lots of zeros in it, then that's your best choice, because most of those terms in your sum will then become a zero. So let's look at an example here. Example 4, we want to find the determinant of the matrix A. So we have a 3 by 3 matrix, and we get to choose what we want to expand along. Do we want to pick a row? Do we want to pick a column? Which one? And so what I want to call to your attention is we have one single zero entry in this matrix. So given the choice of which row or column we want to expand along, we have two good options. We could either choose this first column, or we could choose the second row, right? Either of those are good choices. And so what I'd like to do is I would like to compute it in both ways. So we'll finish off this example doing two different methods, and we'll see that we actually get the same value out. So to begin, let's go ahead and expand, whoops. Let's go ahead and expand along the first column. So I'll kind of call that out here by circling it. And so where we're going to start is we're going to start in the first column and the first row. So our Aij entry, if we're looking up in these equations, our Aij entry is the A11, in this case is 3. So what we're going to have is a -1 to the 1 plus 1 times 3 times, let's clean this matrix up. We want to take the determinant of the strike through or cofactor matrix. So if this is the element that we're working with, we want to strike through its column and row. And what's left over is called the cofactor matrix, which is 4, 3, 2, 7. And we know how to compute the determinant of a 2 by 2 matrix. So now that we're done with that entry, remember, we decided that we were going to go along the first column. So now we move down to the next term. Technically speaking, we would have a -1 to the I plus j. This is the second row, first column. Then our entry in that place is 0. And then our strike through matrix would be comprised of 2, -1, 2, 7. Now, it's silly to even write this all out because we see that there's a 0 in there. So this entire term is going to 0. But I just wanted to write it out so that everybody is able to follow along. And then finally, our last entry in the first column is -5. So we have a -1 to the third row plus first column times that entry, which is -5, times the determinant of its cofactor matrix, which is 2, -1, 4, 3. Now, since we've reduced it to a sum of 3, or actually 2, since one of them dropped out, determinants of 2 by 2 matrices, we can just move forward. So I'm just going to note here that this term is equal to 1 and this term is equal to 1. It's a -1 squared and a -1 to the 4th. So both of those are 1. So what we have is 3 times, let's compute this determinant. 4 times 7 is 28, minus 2 times 3 is 6. Then the next term was 0. And then the final term is -5 times 2 times 3 is 6, minus a -1 times 4 becomes a +4. So in the end, we have 3 times 22 minus 5 times 10. So we have 66 minus 50 for a final determinant of 16. All right, so that was expanding along the first column. Now, looking back up at our original matrix, we noted that 0 also occurs in the second row. So an equally good choice for expansion would be to expand along the second row. So using that vertical bar notation, I would like to compute the determinant of A. And so our first entry in this row is 0. I won't even write out the -1 to the whatever plus whatever, and I won't even write out the cofactor matrix because the whole thing's going to go to 0. So now we're going to move on to the second entry in this row, which is a 4. So where does this live? It is in the second row and second column. So we have a -1 to the 2 plus 2. Then we want to include that entry. And then we want to multiply by the determinant of its strike-through matrix, which is 3, -1, -5, 7. All right. And then the final entry here is in the second row, third column. The entry itself is 3, and its cofactor matrix is 3, 2, -5, 2. All right. So now we can carry out the arithmetic. We have a -1 to the 4th power, which is just a +1. We have 4. And then the determinant of this 2 by 2 is going to be 21 minus 5. In this next term, we have -1 to the 5th power, which gives us a -1 times 3. And this determinant is going to be 6 minus a -10. So I have 4 times 16 minus 3 times 16. If I factor out a 16, that's 16 times 4 minus 3, which is just 16. So you'll see that the value that we got expanding along the second row or column was the same as the value that we got expanding along the second row. You could pick any of these 3 rows or any of these 3 columns. All of them would give you a determinant of 16. So we're going to end this video here at the bottom of page 4. I'll complete a second video over pages 5 through 8 just to kind of break it up. And then we'll start seeing how this matrix algebra is going to be useful in solving systems of differential equations.